Okay, so let's finish up chapter 10, or chapter 10, what am I saying? Chapter 8. Just talking about delocalized electrons and how they affect pKa. As I've been telling you, pKa has a significant effect on reactions, and it can help us determine the electrophilicity of the hydrogen of a molecule and also the nucleophilicity of the oxygen of the acid. So a carboxylic acid, we know already, is a stronger acid than an alcohol. And the reason that it's a stronger acid than an alcohol is because of inductive electron withdrawal and electron delocalization. So the electrons of the two oxygens can be withdrawn to the carbon, or I'm sorry, not to the carbon. The electrons, the oxygens are going to withdraw electrons to themselves. Okay, and that means that the electron density of hydrogen is going to be lower. The electron density of the oxygen to hydrogen bond will be lower, and the bond to hydrogen will be weaker. For the ethanol, the electrons are localized on the oxygen, and so they can't, the second oxygen in the acetic acid means that it can withdraw electrons towards itself as well, including those of the hydrogen that is directly bonded to the oxygen. But in ethanol, the electrons are localized on the oxygen, and the hydrogen is directly bonded to that oxygen. And so, because there isn't a second oxygen atom to also withdraw electron density or to delocalize electrons to, the oxygen to hydrogen bond is stronger in ethanol than it is in acetic acid, and the pKa is higher. Okay, so let's look at some examples. Here we have our relatively stable carboxylic acid and its resonance structure. We also have our acetate conjugate base that has two equally stable resonance structures. The negative charges are at the oxygens, and electrons are being withdrawn to oxygen. All right, comparing other alcohols to alcohols that have electron delocalization. So what is the effect? The only difference between these alcohols, the acetic acid, carboxylic acid alcohol, and the ethanol alcohol is the ability to withdraw electrons. Okay, what if we have the same number of oxygens? So carboxylic acid, ethanol, we had in one molecule 2 carbons and 2 oxygens, and then the other 2 carbons and 1 oxygen. So maybe the oxygen was the big factor. Well, what about if we just have electron delocalization, 1 and then 1 oxygen? In that case, the alcohol still has a pKa of 16 when it's just like ethanol. pKa is about 16 for an alcohol that is saturated with no pi bonds, and the electrons are localized at the oxygen atom. That is, the lone pairs are localized to the oxygen and and the oxygen is the only electron withdrawing atom. With the benzene ring, we have an electron withdrawing oxygen atom, or an electronegative oxygen that withdraws electrons to itself, but the lone pair of the oxygen can also be delocalized into the ring. So the delocalizing the electrons from oxygen into the ring is going to withdraw electrons from the oxygen to hydrogen bond and make the bond weaker. And that's reflected in the lower pKa of phenol. So delocalization lowers pKa. Let's make a note. So you can compare two similar molecules, and if one is delocalized electrons and the other doesn't, then the one with delocalized electrons will have a lower pKa and be more acidic. So it increases, lowers pKa, increases acidity. All right. So we can see in cyclohexanol, for the conjugate base, there is no electron delocalization of the electron pairs. And one of the reasons that a molecule with whose conjugate base has electron delocalization is that it is more stable as an anion because the charge can be spread over more atoms. So for phenol, we have electron delocalization of the alcohol shown at the top, and we're trying to explain why phenol is more acidic. And it's because of this electron delocalization and withdrawing electrons from the oxygen to hydrogen bond into the ring. If you look at the conjugate base of phenol, the deprotonated alcohol, the phenolate ion also has electron delocalization, and the electron delocalization of the ion is actually greater than for the acid. So the base, conjugate base, has greater electron delocalization energy than the conjugate acid. That makes losing the proton favorable because it increases the delocalization energy for the molecule. And that means also that the anion of a conjugate base is a stable anion. So looking at other examples, we have protonated cyclohexylamine with no electron delocalization compared to protonated aniline. Notice we have for the protonated aniline, all of the electron delocalization will be within the ring. Nitrogen here has 4 bonds. It has an octet. We cannot delocalize any electrons to nitrogen. The only thing that this nitrogens can do is to lose a proton. Okay, so what would the conjugate base be? The corresponding amine. Oops. All right. So the deprotonated amines will have a lone pair on the nitrogen. All right. And both of these molecules have the ability to delocalize electrons for both the protonated aniline and its conjugate base. Where protonated cyclohexylamine, there is a lone pair, but that lone pair is not bonded to an sp2. The nitrogen with the lone pair is not bonded to an sp2 carbon, and so the lone pair is localized. So there are no delocalized electrons for either the protonated cyclohexylamine or the cyclohexylamine. But for the protonated aniline, there are delocalized electrons in both the aniline, the protonated aniline, and the conjugate base aniline, which is an NH2 group instead of an NH3 group. And notice that, remember when we talked about resonance figures, we said that the more resonant structures you could draw, the greater the delocalization energy of the molecule. So aniline itself, just not the protonated aniline, but the aniline, because you could draw more resonant structures for it, it has greater delocalization energy than the protonated aniline. And greater delocalization energy of a conjugate base indicates that the acid is a stronger acid than a molecule that has no delocalization. So now we need to remember and add some pKa to our chart if they're not already on the chart, and that is for, we already have protonated acids. Okay. We already have protonated acids, or protonated alcohols, protonated carboxylic acids, and H3O plus on our chart for pKa. So these are strong acids. We have carboxylic acids on our chart. We have protonated amines on our chart. We have alcohols on our chart. What we're doing now is we're adding some molecules with delocalized electrons to our chart. Protonated amines we had at about 11, and now we have a protonated amine that has delocalization energy at 5. And we had all alcohols at 16, but now we have to make the addendum that an aromatic alcohol is going to have a pKa of 10. Okay, and these electronegativity of atoms and the ability to donate electrons or withdraw electrons is going to have a significant effect on acidity of molecules. So moving forward, what we're going to talk about now is we're going to talk about having a di-substituted aromatic ring, where on one side we have a group that has an acidic proton, and at another position there is a group that can either donate electron density or withdraw electron density. So electron donation is going to decrease acidity. It's going to make it a better nucleophile. If I increase electron density, I'm going to become a better nucleophile and a weaker electrophile. And in order to be able to donate electrons, we almost always need an sp3 atom. So methyl groups, oxygen with 2 lone pairs, nitrogen with 1 lone pair. These are going to be able to donate electron pairs to the ring, or electron density to the ring. Whereas electron withdrawal is going to increase acidity because you're removing electron density. And you're making it a better electrophile. Oh, if I could spell. All right, so electron withdrawal increases acidity because we're removing electron density, withdrawing it, and that makes it a better electrophile. of the acidic proton. So let's look at some substituents that withdraw electron density and substituents that donate electron density. Okay, a positively charged atom on a electron dense benzene ring is going to withdraw electron density to itself. And that is because in order to withdraw electron density to itself, it should have a dipole moment where the atom bonded to the ring is more electronegative than the atoms of the ring. So nitrogen is electronegative, more electronegative than carbon. So we have a dipole moment that says that nitrogen withdraws electron density to itself. More so even when it is positive, it's going to withdraw electrons to itself. And so this is not going to exceed the octet rule because we're not physically increasing the amount of electrons at nitrogen. We're simply withdrawing electron density towards nitrogen so that nitrogen is closer to negative charges. We're going to define inductive electron withdrawal is defined as withdrawal of electrons through sigma bonds. So you're going to need to know this definition, and it's going to come up again in OChem 2 and in other chapters, chapter 9, probably 10, I know 18. Yeah, a lot of chapters. Okay, now how about donating electrons by resonance? Donating electrons by resonance is a physical donation of a pair of electrons. Okay, so if we're donating by resonance, we're donating a physical pair of electrons. If we're withdrawing by inductive electron withdrawal, then we're withdrawing electrons through sigma bonds. And if we can also a ring can inductively withdraw electrons to itself if that is favorable. Okay, we'll talk about that later. Donation of electrons by resonance. I have a lone pair on an sp3 atom that can be donated into a ring because the sp3 heteroatom is bonded to, so we're going to say sp3 heteroatom with lone pair bonded to sp2 or sp atom can donate lone pair to sp2 or sp atom. Okay, and what happens when we donate that pair of electrons to the sp2 atom? If the atom that we donate to already has an octet, is that one of its pi bonds will break, because if it's sp2 or sp, there must be almost always a pi bond. And if there's not a pi bond and it's sp2 hybridized, that means that the atom only has 3 bonds and does not have an octet, so donating the lone pair would not exceed an octet. All right, so here we have that an sp3 atom donates a lone pair, and then the pi electrons are moved and localized on a carbon atom. Then this lone pair can be donated to make a pi bond, and this pi bond breaks, and we have a lone pair at this atom. This lone pair is then donated to make a pi bond here, and the pi bond that was already to this carbon breaks and goes into a lone pair at the next carbon. Then the lone pair is donated to make a pi bond back to the original carbon atom that had the pi bond. And the pi bond from oxygen to carbon breaks and the lone pair is given back to oxygen. So that would be resonance donation of a lone pair. So OCH3 is what we call an electron donating group. And electron donating groups are going to make acids weaker acids. Okay, so if we were comparing phenol, which has a pKa of 10, OH, to a phenol ring that had more than just the OH group, that also had an OCH3 group, you would expect that because of the presence of the electron donating group, the proton, the proton of the phenol ring that has the electron donating group is going to have, is going to be less acidic. Because of the electron donating group. So the electron donating group, by donating electrons to the ring, makes the oxygen to hydrogen bond stronger, which means that it's going to have a higher pKa. And we'll relate the values of the pKa's later, but if you learn the trend, the exact value of the pKa doesn't need to be memorized. Okay, how about an inductive electron withdrawal? That's when we have an withdrawal of electrons is almost always because a positively charged atom is bonded to a ring. Positive charge one case, a positively charged electronegative atom or I should say more electronegative atom is bonded to carbon of an aromatic ring. Aromatic. And two, an sp2 atom or an sp atom with a pi bond can withdraw electrons. So when these atoms withdraw electrons towards themselves, if there were, for an example, an OH group, which has an acidic proton on the ring, then the OH group hydrogen would be more acidic. Okay, so here we have a chart of how these different groups affect the ring. And we have on the right side, electron withdrawing effects. And on the right side, electron donating effects. So let's look at the pKa's and compare. And this center column is without either electron donating or electron withdrawing groups. So this is our neutral column. So when we have phenol, and the pKa is about 10, 9.95, if we then add an electron donating group, such as a methyl group, which donates by hyperconjugation, and methoxy group, which donates through a lone pair, the pKa increases slightly. So we go from 9.95 to 10.09 or 10.2. So it's a very small effect, but it does increase the pKa. It does become less acidic. And when we add an electron donating group, or when we add an electron withdrawing group, like a halogen atom, which steals electron density, or an sp2 carbon or an sp2 nitrogen, where you can draw a resonance arrow from the ring to the carbon, from the ring to the nitrogen, so that you have resonance structures where ring electrons are going to atoms outside of the ring. The effect is that the pKa is lowered and the proton of the phenol group becomes more acidic. So we have phenol at 9.95. When we add an electron, a very electronegative atom that's a halogen, and it steals electron density, then the pKa drops to 9.38. When we have an sp2 carbon that you can physically donate electron pairs from the ring to the carbon, the pKa lowers to 7.66. And when we have an electronegative atom that you can show electron pairs from the ring being donated to the electronegative atom, then we have a pKa of 7.14. So the pKa decreases significantly depending on the electron withdrawing group added. For protonated aniline, the acidity of the proton of a protonated aniline, which has 4.58, if we add an electron donating group, then the proton of the aniline becomes less acidic. pKa increases to 5 and 5.3, depending on the electron donating group. And when the pKa of the protonated aniline is 4.58, if we add an electron withdrawing group such as bromine or aldehyde or a nitro group, then the pKa lowers significantly from 4.58 with a halogen to 3.91, and then with the sp2 carbon to 1.76, and with the nitro group to 0.98. And if you remember, acids that have a pKa above 3 are considered weak acids, but acids with a pKa from 1 to 3 are moderate acids, and acids with a pKa of less than 1 are strong acids. Comparing carboxylic acid, which has a pKa of 4.2, when we add an electron donating group, the pKa increases slightly. So you can see that there's a difference in the pKa, it's increasing a little bit. When we add electron withdrawing groups, then the pKa lowers and we get the proton of the carboxylic acid becomes more acidic. Okay, So that covers all of our molecules in group 1. We've covered alkenes, we've covered alkynes, and we've covered dienes. And so we're finished with the reactivity of group 1 molecules. And in chapter 9, we're going to start reactivity of group 2 molecules.